Alright, hi everybody. So what we're reviewing today is electric field and electric potential, which I personally think these are the two hardest topics that we deal with electricity. I think it's just kind of complicated, and it's sometimes tough to see why do we need this? Like, why do we need to define this? We talked about force, so what's the point? So I think that makes it kind of difficult, and it's just very conceptual. It's hard to kind of picture one object acting when we're so used to a bunch. But yeah, so we'll get more into that. What we're doing today is a quick little review. Hopefully I'll try to make it quick, to the point, and fast. And then I have some kind of multiple choice, more conceptual questions, and then some free response questions. Again, the multiple choice, I know we don't have that on the AP test, but they're really good for getting concepts down. So we'll get a few conceptual questions and a free response question, and that all is going to be due on Thursday. So this is going to be Wednesday and Thursday. So yeah, let's jump right in. So we talked about electric force. And we said that by definition, forces, they're interactions between two objects. You need two objects to have a force. So like I lift water bottle, I'm acting on the water bottle. We have these two objects. So in the case of electricity, we have this two objects. We have, okay, here's my object A and my object B. So object B is going to feel a force from object A, and object A is going to feel a force from object B. And we define the electric force, which is a force that acts between two charged objects at a distance. And that's kind of weird because all the forces that we're really used to talking about are these like contact forces. We're comfortable with that. We're saying, hey, I see my hand picking up the water bottle. I know that this happens. I can see it. I see this contact. But here we have this long range force. We have these forces that are from objects that aren't touching. So yeah, it's different than all the other types of forces that we're used to. So we need to think about, how does this work? How does object A know that object B is forcing it, even though these two objects, they're not touching each other? So how does that happen? Do they just go, hey, I'm forcing you now, and the other one's like, okay, that's probably not what happened. It's kind of what happens, but you know. But so what we're going to do this is build up this idea of a field model. So we've done gravitation forces before, and now we're looking at electric forces. And both these forces, they're similar because they act in fields. So we say that objects are physically able to manipulate the space around them. So when we're talking about electric fields, it's because objects have this inherent property of charge, and that charge, this inherent property, affects the field around it. When we talked about gravitational fields, objects have this inherent property of mass, and this mass is affecting the field around it. It affects the space around it and creates this field. So this alteration of space is what's really acting on the object and causing our objects to be able to be forced. So this alteration of space, that's what we're going to call a field. So we can kind of see, hey, this is what we talked about with electric field, and maybe you're used to seeing the gravitational field like this, kind of this warping of space-time, saying this mass is physically bending space-time. That's more of like a general relativity thing. We don't really talk about it, but maybe you've seen it. Maybe you've seen like a science show or science video or whatever, and it's talking about this idea of actually bending the space around it, and that field is what's doing the forcing. And even though we're calling it electric field model, the electric field is real. So even though it's a field model, it's a real thing. It exists. Like you can sense it. We're not able to sense it so much, but like animals use the electric field. Like I was reading a textbook about this, and I think it was really interesting. They said like, hey, platypuses, they have like this thing in their bill, and they're actually able to sense electric fields. And when the fish that they want to eat, they hunt them down and they go, okay, like I can sense the electric pulses coming off these fish, and they can hunt like that. They just close their eyes and then sense it with their beak. Or like bees, I was reading about this too. Apparently bees, they have like the little hair on them, like little bumblebees have like, they're kind of furry. If they go by a flower that has pollen on it, the pollen has these charges, kind of like charging by friction. It's brushed up some charges, brushed up some extra electrons, and they actually feel that pull in their hairs, and they say, hey, this flower hasn't been pollinated yet, I can do that. So they actually have a sensor that can sense the electric field. It is a real thing. Even though we're calling it a model, it is a real phenomena. So the field model, just to kind of lay out this model, it's weird, and this is where the strangeness comes in, is it's more so acting as a predictor. So it's not saying like, hey, this is happening. It's allowing us to make these predictions to say what would happen if we were to put a charged object at a certain location. So what would happen? Because with forces, we need these two objects. We're kind of taking away one of the objects and saying, okay, we don't have the other object that's being forced, but if we were to put that other object at that location, what would happen? So we've done this a bunch with the gravitational field without even knowing it. Like we did it all the time. We said, okay, well this g that we define, this 9.8 meters per second squared that we're so comfortable with, or sometimes newtons per kilogram, which we'll look at in a little bit, this gravitational field, it's something that we're really comfortable with. And it's doing just this same idea. Like this calculation, this force of gravity equals mass times the gravitational field, it allows us to say how much force would an m kilogram object feel if we placed it on Earth's surface. We said, okay, well the gravitational field on Earth's surface is 9.8, and then we just plugged in that m and it told us how much force an object would feel if we knew its mass. So yeah, so when we're looking at this field model, we can say, okay, the source charges are going to be the things that are actually altering the space. So we're going to care about the charged object that's actually creating the field. So every charged object is going to create a field. We're going to say, okay, let's look at this one object and then see what happens when we bring other objects around it, or predict what would happen if we brought other charged objects around that source charge. So the source charge alters the space around itself, and this altered space is called the electric field. And if another charge is placed in the field, it will experience a force that's exerted by the field. So the field is the thing that's exerting the force on this little test charge that we'll bring in to the source charge. So to kind of compare it to what we're used to talking about the Earth as kind of a source mass that's creating a gravitational field. So we know the moon is gravitationally bound to the Earth. So we're saying, okay, well the Earth is creating this gravitational field. If we put the moon in this gravitational field, how much force does it feel? And we can kind of look at this situation. The Earth has this field all around it. The Earth is creating a field. This field exists even if the moon isn't there. But then what I'm doing with the field is saying, okay, well, how much force would the moon feel if I brought it here, or if I brought it here, or if I brought it there, if I brought it there, if I brought it there. So it's really a predictor of saying, hey, how much force would an object feel if we brought it into this field? And so, yeah, with our electric force, or electric field, the kind of going over some variables and some ideas, the variable that we're going to use for the electric field strength is going to be this capital E. So maybe we'll just call it electric field, maybe we'll call it electric field strength, but we're just going to say, hey, this field strength is going to be defined by E. And it's going to be measured in newtons per coulombs. And if we're looking at an equation for this, we can say, okay, E, the electric field strength at a certain location, is equal to the force on a test charge Q at that location divided by the charge of that test charge Q. So Q being a charge that we'll bring in. And then if we kind of move this equation around to kind of mirror this gravitational equation that we looked at, we can say, well, F is equal to Q times E, the same way that our gravitational force is equal to M times G. So the object that we're bringing into the field, the test object, either test mass or test charge, times the field strength is going to equal a force. So if we look at this situation that we've kind of set up, let's say that we have this source charge of this positive source charge. I didn't give it a charge, but we have this positive source charge, and at this location right here, let's say that it creates an electric field of 5 newtons per coulomb. So now what we're able to do, now that we've defined the electric field at that location, we can say, well, what happens if we bring a 2 coulomb charge at that location? Well, we're bringing a 2 coulomb test charge at that location. We know that if we did bring it there, it would want to be forced away. It would follow this electric field, the field line that we've set up, right? Because positive objects are going to repel each other. And we can very easily say, well, we see this is going to feel, or the field is creating a field, or the source charge is creating a field of 5 newtons per coulomb at this location. So if we bring a 2 coulomb charge in there, we'll have 2 coulombs times 5 newtons per coulomb, and that 2 coulomb test charge will feel a force of 10 newtons. It's feeling 5 newtons for every coulomb that we bring in there. So we can do the same thing, and the reason why defining the electric field is so helpful is because we're able to change it up so easily. We're able to say, okay, well, this is just a predictor of what would happen if we brought something into that space. So before we're bringing a 2 coulomb charge in there, what would happen if we brought an 8 coulomb charge in there? We could figure that out really easily. It's helping us make these predictions. Well, we know, okay, there's 5 newtons for every coulomb that we bring in there. We're bringing 8 coulombs. So that 8 coulomb test charge would feel a force of 40 newtons from the electric field. So the electric field would force it with 40 newtons, and that electric field is created by our source charge. And again, just kind of comparing it, this is what we do on the Earth all the time. We say, okay, well, we're looking at some distance away from the center of the Earth. And yeah, we did this all the time. We said, okay, well, the gravitational field strength on Earth is going to be 9.8 newtons per coulomb. And we said, okay, well, we can find out the force of, say, a 5 kilogram object by doing F equals m times g. And we're able to figure that out really, really easily. 5 times 9.8 is going to be 49. And then let's say we bring in a different mass, a mass of 10 kilograms, or a mass of 15, or a mass of 1,000 kilograms. We're able to figure out how much force that field is giving to the object. So again, we've done this before. Every time we found the gravitational force, we've done this. We've used this idea of fields. And then what we want to do is we want to be able to visualize the electric field around our object, because this is going to be helpful. This is going to help us really make predictions. And our drawings won't always be perfect. They won't always be to scale. It'll be kind of hard to draw them. But it helps us think about what would happen if we were going to bring a charge in there. What path would it take? How would it move? Would it move in a straight path? Would it curve? Who knows? So we want to think about what kind of path would this object take if we were to bring a test charge into this electric field. So again, we said the electric field is going to alter the space around a charged object, and we can visualize it with a vector field. And a vector field is really nice to help us visualize this, because we've talked about vectors before. They are mathematical things. I don't know, it's not a great explanation for it, but they are mathematical ideas that have a magnitude and a direction. So we can represent how strong the electric field is by how long the vector we draw is, and we can represent what direction the field would move a test charge by just drawing the direction of the field. So we see over here, if we were going to bring a positive test charge next to this positive source charge, it would move away from it. So it would follow these electric field lines. We see if we put it at this location, it would feel a weaker force because there's a weaker field than if we put it at this location because there's a stronger field. And then if we brought a positive test charge by this negative charge, we know that it would be attracted to the negative charge and it would want to move towards it. So we see, hey, we have this direction, and then the magnitude also matters. And I just kind of went over this, but when we're drawing electric fields, we're going to use this convention of kind of predicting what would a positive test charge do if it were placed near the source charge. So the direction of our field lines are always going to be based on what would happen if we brought a positive charge into this field. So it'll go away from positively charged objects and then towards negatively charged objects. So the field is defined as what would happen if we were going to bring a positive test charge Q near that source charge. And then just kind of looking at different configurations, electric field of a point charge, or configurations and equations, I guess. So we know that the electric field would kind of look like this. It would be kind of strong when we get closer to our source charge and then weaken as we go away. And this is really all coming from, if we're looking at the equation, if we're looking at the distribution, it's really coming from this idea that, well, if we had a source charge Q and then a little test charge of lowercase q, if we brought them next to each other, they would feel this force. And then what we do when we look at the electric field is we're saying, well, let's not worry about this test charge lowercase q. Let's not worry about it. Let's define this quantity based on the source charge, this capital Q. So we know that for a single charge, the force, or for like a point charge, the electric force is going to be this 1 over 4 pi epsilon naught, Q1, Q2 over R squared. And then just to help us kind of visualize things, let's instead call Q1 and Q2, let's call it capital Q for our source charge, and then lowercase q for our test charge. So we got big Q, lowercase q over R squared, just replacing these little q's. And then we're saying, well, we want to define a quantity for the source charge. So let's just divide out our test charge. Let's take our force equation and say, well, I don't want this lowercase q in there because I don't care about the test charge. I could bring in any lowercase q. That's what I want to really figure out. How much force would any charge feel? So we're just going to divide out that test charge. So we're saying, okay, let's take our force equation, divide out this lowercase q that won't even exist when we look at it just in a field. So we're dividing that out and defining this quantity based solely on our source charge. So if we look at the equation that then comes out of that, we get 1 over 4 pi epsilon naught times this source charge q, uppercase q, divided by R squared. And we've defined this quantity based solely on the source charge and not the test charge. So we've divided out the test charge. And if we look at this equation here, if we multiply both sides by the test charge lowercase q, we get E times lowercase q is equal to the force, which is the equation that we talked about on these slides and the ones we used. All right, so then what if we have more than just one charge? That's totally okay. The electric field is a vector field, and we said that we can add vectors. Like, we've done a bunch of stuff with vectors before, whether it was through forces or like velocities or momentums. Yeah, momentum. We can add vectors. We know how to do it. We add vectors kind of based on just the dimensions. We say, okay, we can add the horizontal components and the vertical components, and then use the Pythagorean theorem to add up vectors. So I don't remember why I have this pulled up. Maybe just to kind of show the distribution. Oops. Is that all his lags? Okay. But so we can kind of create these distributions and visualize these electric fields when we have more than one charge. All it is doing is it's just kind of superimposing the electric field of all of our objects onto each other. That's effectively what it's doing. But yeah. So if we had something like a positive charge and a negative charge right next to each other, we'd see, okay, well, we kind of have this attraction, like push from the positive side and then attraction to the negative side, and we'd kind of see that trend throughout our field. Yeah, so when we have kind of these different configurations, it gets more complicated, but it really is just kind of a vector field. It's just saying, hey, let's add these electric fields together. So some significant configurations, some spots where that gets a little bit complicated or a little bit tricky, is parallel plates and then conductors. So parallel plates are what we talked about when we kind of think about a capacitor. We have one plate is positive, one charge is negative, and when we do that, we get this really nice uniform field, this uniform electric field where we have a constant value of the electric field between the plates. So everywhere we look at it, we'd say, okay, the value of the electric field is this. So it's not changing with distance. We're just saying, okay, between these two plates, what is the value of the electric field? And it'll be constant. Just like kind of how on Earth we say, hey, locally, if we're looking at just the surface of the Earth, we have a uniform gravitational field on the surface of Earth. And we say, okay, well, that gravitational field locally is straight down, and it's going to be 9.8 newtons per kilogram. So the way that we get to this is if we say, okay, let's have a bunch of positive charges in a row, and let's have a bunch of negative charges in a row, just like we do when we have these plates. Well, we see we have a lot of cancellations. If we're kind of drawing this circular distribution, we see, okay, well, all of these, this up distribution, or this up field is going to cancel this down field on this side. Up is going to cancel down, up is going to cancel down. And then we can split into components and say, well, this rightwards component and these rightwards components, those won't cancel. But here we have a downwards component and an upwards component. So all of our components will cancel, and we're really left, well, all of our upwards, downwards components will cancel, and we'll be left with this nice uniform distribution, this nice uniform field. And our equation for this, we don't have to know how to just to find it. Eventually you'll do electric fields with calculus, and you'll have to like make these boundaries, and you'll do these Gauss boundary stuff, and it's a mess. Gauss's law, that's what it's called. We don't have to do that, which is nice. So we can just say, hey, the electric field is equal to Q over epsilon naught times A. And Q is just going to be the charge on one of the plates, and then A is going to be the area of one of the plates. Excuse me, sorry. So when we used this equation before, a lot of us, we put in 2Q because we wanted to look at the total charge. We don't have to do that. This equation, it kind of figures that out for us. We just had to figure out the charge of one of our objects. So just Q on one of the plates. And then conductors. So I don't remember if we talked about this before, but this is kind of a big idea. This idea that the electric field is 0 at all points inside of a conductor. So we talked about conductors before. We said when we have a conductor, and we add electrons to it, the electrons will spread out throughout the surface of the conductor because these electrons, they repel each other and they don't like being by each other. So they're going to spread out in a way to kind of maximize the distance between each other. And when that happens, the electric field inside of it is going to work to cancel itself out. So they're nice and symmetrical, and through that symmetry, we're going to have a lot of canceling inside of our conductor. So, and then when we get to the surface, it's going to be perpendicular to the surface, the electric field will be. But so this is kind of a very simplified situation. Of course, like if we had a sphere or something and we cut it in half, we would have a lot more than just 4 charges kind of spread out. But this is just simplifying it. So if we look at this situation, we'd say, well, I see I kind of have This leftwards piece is canceled out by this rightwards piece. This upwards piece is canceled out by this downwards piece. This diagonal is canceled out by the other diagonal. This diagonal is canceled out by the other diagonal, so on and so forth. But we'd get this canceling all within, so the electric field inside of a conductor is going to be 0. And now I know what you're thinking. You're thinking, okay, well, I get electric fields, they're great, but what would happen if we were to move a charged particle along an electric field line? What happens if we start to bring particles into these fields and we move them around? I know that's the burning question in your minds. So let's picture this situation. Let's say we have a source charge, and then we put a little test charge in here. Again, this test charge is defined to be positive, so let's put a little positive test charge in this electric field created by the source charge on the left. So we'll bring it in there, and we know that that little test charge, it will feel a force, and the strength of that force will be in accordance to the strength of the electric field. But so it'll feel a force, and yeah, it'll feel a force. And if we wanted to move it, if we wanted to take this little test charge and move it closer to the source charge, we would have to apply a force to it. We would have to say, okay, we have this system of these two test charges, or sorry, one source charge, one test charge. We have this system. We'd have to bring this outside force in here to then move it closer to that source charge. So in this case, we kind of have this hand, and it's applying this force in the opposite direction to move it closer to the source charge. And in this push, we displace this source charge. It becomes displaced by some sort of outside force. And when we get it closer, now it feels a greater force than it did before. It has this greater force acting on it, and it's going to want to move more. Now it has kind of more of this stored energy. We'll look at a similar situation in a second, but before it just had a little bit of force acting on it, now it really wants to move away. We know that these two are like charges, they're both positive, and they want to repel each other. So by moving it closer to the source charge, we're increasing the amount that it doesn't want to be there. It's going to want to move away a lot more. So what we really did in this situation, hopefully I used some terminology that kind of like, oh yeah, for you. But so I said, hey, we have this outside force displacing an object in our system. And when we talked about energy before in your previous physics classes, we said that that's kind of our definition of work. This idea that we have this outside object forcing something in our system over some displacement. So we kind of look at this situation. Well, this little test charge, it had this potential, this electric potential energy associated with it. If we kind of put it in this field and held it there, it has this stored energy. It would want to convert this stored electric potential energy into kinetic energy. It would want to move away from our source charge. By moving it closer, by forcing it over some displacement and moving it closer to that source charge, we're increasing the amount of electric potential energy that it has. It would want to move away a lot more. It would then have a larger kinetic energy because it doesn't want to be there. It doesn't like being next to it, so we have this repelling. It would want to move away. So we did work on our system, and we changed the electric potential energy of our system. And this is kind of the same exact thing that happens when we compress a spring. This is kind of how I like to think about it. The spring, it wants to be at its nice equilibrium position. If you take this mass and you kind of compress it on the spring, you're doing the same thing. You're storing energy in that spring as opposed to storing energy in the electric field, but you're storing that energy, and that object would want to move away and convert this stored energy to kinetic energy. So it's kind of the same exact idea. Or another kind of like situation that we're going to compare a lot of this to is the gravitational field, something that we're really used to. If you drop a ball in this gravitational field, it will feel this downwards force. If you lift it up over some sort of displacement, you're doing work on it, and you're increasing its potential energy, its gravitational potential energy, which we can then convert to kinetic energy. And kind of going along with this gravity analogy, let's look at a situation where we take a 2-kilogram ball, it's sitting at 0 meters, and then let's lift it up to 5 meters. And we say, well, we know our equation for gravitational potential energy. It's just mg times the height. So we say, okay, well, we have this gravitational potential energy of 2 times, let's just use 10 instead of 9.8, times 5. We gave this ball, by lifting it up 5 meters, this 2-kilogram ball, we gave it 100 joules of gravitational potential energy. And let's do the same thing, but now for a 6-kilogram ball. We take this 6-kilogram ball, we lift it up 5 meters, and now it has this, well, not now because it's a different ball, but this ball has a gravitational potential energy of 300 joules. 6 times 10 times 5 meters. So 300 joules of potential energy. And if we did it with a 15 kilogram ball, we'd say, okay, again, same thing. We lift it up to 5 meters. Now it has, or this one has 750 joules of potential energy to do work with. So if we're looking at this situation, we say, okay, well, for 2 kilograms, by moving it up to 5 meters, this thing now has 100 joules. For 6 kilograms, it has 300 joules at 5 meters. For 15 kilograms, it has 750 joules at 5 meters. And then what we can say is, well, if we look at this, we have this gravitational potential energy, we have this mass, we can define this quantity that's the same for each of these things. Even though we had 3 different balls, they were all up to the same height. We can define this quantity that is a property of the height above the ground. So in this case, we say, okay, well, let's take the gravitational potential energy and divide out the mass. So we have 100 joules divided by 2. That's going to be 50 joules per kilogram. If we do it for the 6 kilogram ball, we say, okay, well, this location of 5 meters also has 50 joules per kilogram. If we do it for the 15 kilogram object, 50 joules per kilogram at that 5 meters. So what's cool is we've kind of given this location of 5 meters this quantity. We can say any object at this location of 5 meters off the ground will have 50 joules of gravitational potential energy for every 1 kilogram of mass. We've defined this ratio that is a property of the location. And this ratio that's a property of the location, this can be called our gravitational potential. We don't use gravitational potential a lot, but it's something that we could define if we wanted to. The thing that's more important is going to be us defining electric potential, and it's really similar. We were just looking at gravitational potential to help us build that up. But electric potential, it works in a really similar way, but we use it a lot more often because we usually don't want to think about individual charges moving. We just want to think about, okay, if we were to put a charge in here, how much energy would it have? Because we don't usually know how much charge is like moving through our circuits or in our battery. We care about more of a property of the location. So in this case, let's say instead of the ground being a height of 0, let's say this point A has a voltage, which we'll talk about in a second, of 0 joules per coulomb. If we were going to move it from A to B, where B has a voltage of 400 volts or 400 joules per coulomb, what we can say is, well, we took a 2 coulomb charge and we moved it from A to B. We gave it 400 volts. We gave it 400 joules for every 1 coulomb that it has. This situation, we happen to be moving a 2 coulomb charge closer to that source charge, so we can really quickly figure out and say, okay, well, now it has 400 joules per every coulomb that it has. We had 2 coulombs of charge, so we just gave this little object, we gave this test charge 800 joules of energy, of this electric potential energy. And we could do the same thing, again, like we did with field. We said, well, it's a property of the location. It's a property of our source charge. So if we were looking at a 6 coulomb charge, let's say we take our 6 coulomb charge, we move it from A, which has a defined 0 joules per every coulomb at it. We move it from A to B, where B, again, property of the location, it's the same location, it's still point B, has a defined 400 joules for every coulomb that we move there. So we have 400 volts at location B. So we go from 0 to 400. So we gave this charge, the 6 coulomb charge, 400 joules for every coulomb that we moved. In this case, we moved 6 coulombs. So we gave this 6 coulomb charge 2,400 joules of electric potential energy. So when we're thinking about electric potential, that was kind of a mathematical example, but I think it helps us kind of visualize why we're doing this and what's going on here. A definition that I like for electric potential energy, it sounds kind of confusing at first, but the more you think about it, kind of the better it gets. But a good definition for electric potential is the potential for creating potential energy. So it's kind of saying, if we were to do this, if we were to move a something coulomb charge at this location, how much potential energy could it have? So the potential for creating potential energy. How much could a charge have if we moved it from one location to another? And we can think about it as a property of the location. So if we were to bring, I'll just kind of read this. If we were to bring a certain number of coulombs charged object to this location, how much potential energy would the charged object gain? That's one way to think about it. And one of the main really important parts is this idea that the electric potential is created by the source charge, and it's a property of the location around that source charge. So again, just like we saw with the field, it's created by the source charge, and it's a property of the location. We can pick out a point and say, at this point, this is the voltage. This is the potential at this location. And yeah, I'm going to use them kind of interchangeably. The symbol for electric potential is V, and the unit is joules per coulombs, or what we're more used to, voltage. And then we have this equation, the change in electric potential energy is equal to the little test charge that will move, so the value of the test charge, times the change in voltage. In this case, we went from 0 volts to 400 volts, so our change in voltage was just 400. And then it's a little bit weird. We just kind of talked about this change in voltage. So one thing that we're going to have to do is define a position of 0 potential. A lot of the times it'll tell us to treat like a certain location 0, but we kind of have the same issue when we look at gravitational potential energy or gravitational potential. Like if we have a ball that's sitting on a table that's sitting on like a building or something, we need to think about, well, what are we going to call 0? What can we call 0 potential energy or 0 potential? So that's just something to think about. Usually it'll tell us where 0 potential is, but there's really no like 0 potential. We're looking at if we move a test charge from one location to another, how much did the potential change by? So with this case, regardless of what we call 0 height, if we move from one location to the other, the change will be the same. If we call this, let's say this is 10 meters off the ground. If we call this 0 and this 10, if we move it from there to there, we still move it 10 meters. If we call, I don't know, this 0 up here and this negative 10, when we move it from the ground to the building, it's still undergoing a change in location of 10 meters. So this change, something that's important, something to think about when we think about what is 0. So changes in potential, electric potential and gravitational potential are similar to each other because they're both properties of the location. Just like we did way back here, we said, okay, well this height, we can call it, we can say this 5 meters is a potential of 50 joules per kilogram. Just like here, we can say, oh, point B is 400 joules per coulomb. So it's a property of the location. And we can use a common kind of marker of gravitational potential to help us understand electric potential. And that idea is topographic maps. So I know we talked about this a lot when we were in class, but so topographic maps are a helpful tool that kind of show us, I think I deleted one of my slides. That's okay. That doesn't matter. But so yeah, so we can say, okay, on this topographic map, there's these little circles, these continuous lines, these continuous circles that denote a line that has the same height. So if you were going to hike this, every time if you were walking around this one single line, you'd be at the same elevation. So it kind of helps us visualize, like, hey, how steep is this hike going to be? If we see all of these lines really, really like spaced together really closely, it means we have this like sharp change in elevation. And if it's more shallow, then we kind of have this flatter surface. But so we can call those isolines. These locations are these lines that show us the same potential, the same height. So we can do the same thing with, if two objects are at the same elevation, then they have the same gravitational potential. So we just said gravitational potential is a property of the location. So if we're at the same height, this thing that's going to help us define gravitational potential, then we're going to have the same gravitational potential. So if we have these two objects that are the same isoline at the same height, then they have the same potential. And if we actually change, if we move through isolines, if we move from one to the other, then we are changing the amount of potential. So we'd have to do like work on our system to do that. If you were doing it, you would have to walk, you'd have to work against gravity, you'd have to physically force your body up this hill to, that sounds way darker than it is, you'd have to walk up the hill, you'd have to force yourself through this displacement, do work on the system to change the energy in the system. So moving from here to here, in terms of energy, that's free, that doesn't cost a thing, that takes no work because we end up with the same amount of potential at each case. We have the same amount of joules per coulomb or joules per kilogram in each of these cases. So this is kind of a free move. If we move along an isoline, that takes no work. If we move against an isoline or through isolines, that's where work comes into play. That's where it takes energy to do that. So just kind of final things, I think, yeah. if we kind of look at any situation, let's just kind of set up a few of these. Set up these. We can use this little tool to help us actually mark isolines. So we can say, okay, let's try to get a nice even spacing. I should have done this before and then trying to go down by 10. All right, whatever. But so we see here, when we get closer to this source charge, it's going to take a lot more energy to move a smaller distance. It'll take a lot more work to do that. We'd have to move through more voltage. When we're over here, we feel kind of less of this electric force. We're working through less electric force, so it's going to be easier for us to work against. It's going to be easier for us to change our electric energy by doing work on an object to move it through this field. But yeah, just kind of like quick little wrapping up notes. The electric field at a point is perpendicular to the equipotential line at that point. We'll look at that in a second. The electric field points in the direction of decreasing potential, and we can relate E and V, electric field and potential, by this equation. E is equal to V over R, so this, where R represents the distance we're moving through the field. And just kind of going back to this and looking at it, we see at each of these locations, the electric field is perpendicular to our isolines. And if we move along this electric field, that's where we start to see this change in potential, this change in energy effectively. And yeah, that's kind of, oh, and then we want to kind of look at these different distributions. For a uniform electric field between parallel plates, electric field is pointing like this, and our isolines, our equipotential lines, are going to be perpendicular to the field. Same here, when we have a point charge, this circular distribution, the isolines are circular. And when we have more complex situations, it's going to be a little bit harder, but we can draw them in by just saying, oh, well, it's always going to be perpendicular to the field. So yeah, that's what I got for today, and then I'll give you some practice stuff.